All right, we're going to be focused on the unit step function. In particular, we want to solve ODEs, and we're going to use Laplace Transform. So the idea is we have something we're calling the unit step function, and we've defined this thing to be 0 if t is less than a, and it's 1 if t is greater than a. So you can think of this thing as 0 until you get to t equals a, and then it flips into an on state. So it goes from off to on and is equal to 1. So graphically, until the thing is off or 0, until we get to a, and then at a, it becomes equal to 1. We also have, from last time, this following property, that the Laplace transform of a function evaluated at t minus a times a step function evaluated at t minus a is e to the minus sa times the Laplace transform of the function. And we can use this to solve DEs, and it's nice because I can just go through and just brute force my solution by just using properties of Laplace transforms. If I did not do this, if I had something like this, I'd have to find the solution to a differential equation until I got to t equals a, and then I'd have to stop and redo and find the solution to a different differential equation after that, and then I'd have to find a way to bring things together. Okay. So this is a really nice way to work with things, situations where you have things turning on and off. Right. Now, one thing I want to be a little bit careful of is that this is when we go backwards, we're going to have the Laplace transform of the original function, but then when we try to figure out what this function was inside, we're going to have to evaluate it at t minus a. So it's going to be a little bit of an issue. So let's look at an example. Basically, I'm just going to start looking at examples. There's really nothing new here. It's just applying what we've already seen. So suppose we have y prime plus 3y is equal to h of t, and at t equals 0, y is 2. And h of t, we're going to assume is 0 for t less than 4, and then after 4, it goes to an on state and becomes equal to 5. All right, so that means I'm going to have to write my h of t as a unit step function. So it's going to be 5 times the step function evaluated, this should be 4, evaluated at t minus 4. All right, so the idea is that this function is off until t is less than 4, and at t equals 4, it goes to an on state and is equal to 5. So now, coming back to this thing, I can just take the Laplace transform of both sides. So Laplace transform of the left is Laplace transform of y prime plus 3y. And this becomes 5 times the step function at t minus 4. This becomes Laplace transform of y prime plus 3 times Laplace transform of y. And this is going to become e to the minus 4s times the Laplace transform of 5. And notice I don't have a t in there, so I don't have to worry about any of the t minus 4 nonsense. So this is a special case. Just be very careful about that. So my properties of Laplace transforms is that this is going to be minus y of 0 plus s times Laplace transform of y plus 3 times Laplace transform of y. It's going to be e to the minus 4s, and the Laplace transform of 5 is 5 over s. So I can add this to both sides, so that's equal to minus 2. And notice I've got a Laplace transform there and there. My goal is to solve for the Laplace transform of y. So from these two terms, I can factor out a Laplace transform of y. If I add that to both sides, I'm going to get 2 plus e to the minus 4s times 5 over s. Now divide both sides by that. I get the Laplace transform of y is 2 over s plus 3 plus e to the minus 4s times 5 over s times s plus 3. Okay, that is no problem, because the Laplace transform of 2 e to the minus 3t is equal to that. This is not so simple. It's not quite clear what that's going to be. And because of that, I know it's going to look like the Laplace transform of something times a step function at t minus 4. The question is what's the something? And the something has to be evaluated at t minus 4. So let's see. Let's rewrite that. Laplace transform of y is 2 over s plus 3 plus e to the minus 4s times 5 over s times s plus 3. Okay. I have no problem with that. I can deal with that. Let me focus on this. Right, that is 5 over s times s plus 3. We use partial fractions. Right, this is a over s plus b over s plus 3. Multiply both sides by s times s plus 3. So the s is going to cancel, so I'll get a times s plus 3. Here the s plus 3 will cancel, so I get b times s. So if I let s equal 0, I'm going to get 5 equals 3a. So a is 5/3. If I let s equal minus 3, I'll get 5 equals minus 3b. So b is minus 5/3. So plugging that back into this expression, Laplace transform of y is 2 over s plus 3 plus e to the minus 4s times the quantity. Let's see, a is 5/3 over s, b is minus 5/3 over s plus 3. So this is 2 over s plus 3 plus e to the minus 4s times 5/3 over s minus e to the minus 4s. So I'm just multiplying through by that, times 5/3 over s plus 3. Okay, again, Laplace transform of 2 times e to the minus 3t gives me this expression. This is the Laplace transform of 5/3. And just like this is the Laplace transform of 5/3 times e to the minus 3t. So my y, this is going to be 2e to the minus 3t. Now I'm going to have my 5/3 evaluated at t minus 4, but there's no t there, so I just leave it alone, times a step function at t minus 4, and that comes from this expression. Now for this part, I'm going to have minus 5/3, and here I'm going to have e to the minus 3t, but it's not going to be t. I have to evaluate it at t minus 4 times the step function at t minus 4. Okay. All right. Let's look at one more example. This is going to be a circuit. So we have some voltage source. Oops. So I've got a circuit with a capacitor and a resistance. The capacitance in the capacitor is going to be 3 times 10 to the minus 5 farads. And the resistance is going to be 5,000 ohms. And I'm going to assume that the battery initially is putting out 8 volts, but after 12 seconds, it drops down to 0 volts. And I'm going to assume that the initial charge in the capacitor is 0. This is going to be 0 coulombs. All right, so the idea is we've got this RC circuit. We give it 12 seconds, we give it 8 volts, and then we just turn the voltage off and just let it discharge. And the question is what happens? First thing I'm going to need to do is I'm going to need to write my voltage in terms of step functions. What is it doing? So initially it's at 8 volts, and it continues at 8 volts, and then it drops down to 0 volts. So I initially have 8 volts. After 12 seconds, I have to subtract those 8 volts. So my voltage I can write is 8 minus 8 times the step function evaluated at t minus 12. And now applying my Kirchhoff's loop rule. So starting here, as I go across there, I'm going to have an increase of voltage. But then as I go across the capacitor, my voltage is going to go down by Q over C. As I go across the resistor, so I'm assuming that my current is going in this direction, I'm going to have a drop in voltage given by the current, which is Q prime times R. Now I'm back to here, and that's going to be equal to 0. All right. So let's see what we have. So my voltage is 8 minus 8 times the step function valued at t minus 12. My capacitance is 3 times 10 to the minus 5. And my resistance is 5,000. And that has to equal 0. All right, let me do this. Let me add this to both sides. So if I do that, I'm going to get 8 minus 8 times the step function at t minus 12 equals 1 over 3 times 10 to the minus 5 q plus q prime times 5,000. Let me clean that up one more time. I'm going to write this as 10 to the 5th over 3 times q plus 5,000 times q prime. Right, now I'm just going to take the Laplace transform of everything. I'm going to get the Laplace transform of 8 minus 8 times the step function at t minus 12. And then this is going to be 10 to the 5th over 3 times the Laplace transform of the charge plus 5,000 times the Laplace transform of the current, which is the derivative of the charge. And this whole thing I can write as minus q of 0 plus s times the Laplace transform of q. But notice my q of 0 is 0, so that's going to go away. So let me rewrite that. I have the Laplace transform of 8 minus the Laplace transform of 8 times the step function of t minus 12 is equal to 10 to the 5th over 3 times the Laplace transform of q plus 5,000 s times the Laplace transform of q. All right. So now, just start taking Laplace transforms. Laplace transform of 8 is going to be 1 over s. Because of the step function at t minus 12, this is going to be e to the minus 12s times the Laplace transform of 8. And I'm trying to find the Laplace transform of q to isolate that. So I'm just going to factor that out. So I can factor out a 10 to the 5th over 3 plus 5,000 s, all times Laplace transform of q. And I want to get this, so I'm going to basically divide by that term. So if I do that, I'm going to get the Laplace transform of q is 1 over s, then times 10 to the 5th over 3 plus 5,000 s. So that comes from that term. This term, I'm going to have e to the minus 12s. Laplace transform of 8 is going to be 8 over s. Then I'm going to have to divide by 10 to the 5th over 3 plus 5,000 s is all equal to the Laplace transform of q. All right, and I already have that there. Okay. I'm not thrilled with that, because I know that if I have something like that for the Laplace transform, I'm going to get e to the minus at. So I would like for my coefficient on s to be 1. So here's what I'm going to do. Let me rewrite it. So I have this term, and minus 12s times the same thing. I am going to multiply by 1 over 5,000, so that I'll get a 1 there. But if I divide by that, I have to multiply it. I'm going to do the exact same trick for this term for exactly the same reason. And in doing so, this now becomes Laplace transform of q. It's going to be, why do I lost an 8 right there. That should be an 8. And then I lost it. Oh, I kept it there. So this should be, this term should be an 8. And that term should be an 8. And then I lost that right there. So this is why it's so important to check your work and try to be somewhat neat. All right, so this becomes 8 over 5,000 from this term and this term times 1 over, if I multiply this through, I get s. This becomes 10 to the 5th over 3 times 5,000 plus s. And this becomes 8 over 5,000 from this term and this term. Carry that term down, so I get e to the minus 12s, all times 1 over s. And this becomes exactly the same things I have up there. I've got 10 to the 5th over 3 times 5,000 plus s. So let's rewrite that. Laplace transform of q is 8 over 5,000, times 1 over s. I'm going to have 10 to the 5th over 15,000 plus s plus 8 over 5,000 e to the minus 12s. 1 over s times 10 to the 5th over 15. That's 15,000. Is that right? Yeah, 15,000, because that's 3 times 5,000 plus s. All right. Okay. I think we're okay now. Both of these terms have something that looks like 1 over s times 10 to the 5th over 15,000 plus s. Let me clean that up a little bit. So 10 to the 5th is what, 100,000? Divided by 15,000 plus s. Okay. So this becomes 1 over 100 over 15 plus s. Whew. All right. All right, so 1 over s times 100 over 15 plus s. I don't know the Laplace transform of something that gives me that, but if I expand this using partial fractions, then I know I'm going to get a constant, and I know I'm going to get an exponential. So I can deal with that. So let me multiply both sides by this denominator. These s's cancel, so I'm going to get a times 100 over 15 plus s plus b, then this cancels, so I'm going to b times s. So if I let s equal 0, then 1 equals a times 100 over 15, so a equals 15 over 100. If I let s equal minus 100 over 15, I get 1 equals, this becomes 0, plus minus b times 100 over 15, so b is minus 15 over 100. So I'm going to rewrite this term now, where each of these things I can write as a over s. Where's a? So this can be 15 over 100 times 1 over s plus b. So this can be minus 15 over 100 times 1 over this thing here, which is 115ths plus s. So what does that look like? That looks like now the Laplace transform of q. I'm going to be careful here. So that's 8 over 5,000 times the quantity. And we just said that's a over s. So that's going to be 15 over 100 times 1 over s minus 15 over 100 times 1 over 100 over 15 plus s plus 8 over 5,000 times the same thing. So I get 15 over 100 times 1 over s minus 15 over 100 times 1 over 115ths plus s. Oops, and I forgot the e to the minus 12s. Okay. This one is just a regular, straightforward inverse Laplace transform, right? That's going to give me 1. Laplace transform of 1 is that. And that looks like the Laplace transform of e to the minus 100 over 15t. Here it's going to be the same thing, but because of that term, I'm going to have a step function of t minus 12. And so this looks like 1. This looks like Laplace transform of e to the minus 100 over 15t. But everywhere I see a t in these expressions, I have to replace it with t minus 12. So my q then is going to be 8 over 5,000 times the quantity 15 over 100 times 1 minus 15 over 100 times e to the minus 100 over 15t. Okay, and now for this term, I'm going to get plus 8 over 5,000 plus correct? That plus is not correct. Sorry. Looking here, this should have been a minus because of that term in my previous work. So this should be a minus. So now this becomes 15 over 100 times 1. Notice I'm evaluating at t minus 12. This becomes 15 over 100. E to the minus 100 over 15. But now, instead of evaluating at t, I evaluate this at t minus 12. And there is my solution.